And the topic for this video is going to be finding possible rational zeros of a polynomial. And so what we're going to be looking at is if you have a polynomial that is not in factored form, how do we find out where does this graph cross or intersect the x-axis? And this is going to be generating a list of possible zeros for that polynomial. So the first thing we're going to do is find out what are the factors for the constant term, and we're going to divide that by the factors of the leading coefficient. So the factors are going to be in the numerator all the numbers that will divide evenly into a positive 8, which are going to be plus or minus 1, because a positive 1 and a negative 1 will both divide evenly into an 8, plus or minus 2, plus or minus 4, and a plus or minus 8. And then your leading coefficient on this polynomial is 1, so the factors for that leading coefficient are just going to be simply plus or minus 1. Now we can simplify this down by taking the first number and putting it over your denominator, so 1 over 1, and then 2 over 1, and then 4 over 1, and then 8 over 1. So 1 over 1 is just 1, and that's also a plus or minus 1. Then 2 over 1 is 2, and then we have 4 and plus or minus 8. Alright, so this is our list of possible rational zeros, meaning this graph is going to intersect the x-axis at some place, and most likely more than once. If the intersection values are rational numbers, then they will have to come from this list of rational numbers that we have generated right here. Now there's a nice little theorem in algebra called the remainder theorem, and the remainder theorem says that whatever value we substitute in for x can also be found by looking at the remainder for synthetic division. So, for example, if I take the number 1 and I divide it into this polynomial, 1, negative 2, negative 9, 2, and 8, and just do your synthetic division, you find out that your remainder is equal to 0. Now what that means is that if you took this 1 and substitute it in for x everywhere in this polynomial is going to end up with a value of equal to this remainder, which is 0. So let's try it. Y equals 1 to the 4th minus 2 times 1 cubed minus 9 times 1 squared plus 2 times 1 plus 8. That's going to give us 1 minus 2 minus 9 plus 2 plus 8, and this does come out to be 0. So anytime you take a number and divide it into a polynomial, whatever that remainder is, that is also the value you would get if you substitute that number into the polynomial in for the variable. Now that's going to be useful because what we have right here, we have generated a list of possible zeros. Now, zeros are your x-intercepts, and your x-intercepts all have a y value of 0. So what we're trying to do is, if I plug 1 into my polynomial, do I get a 0? If I plug -1 into my polynomial, do I get a 0? And do the same thing with each one of these numbers, the positive value and the negative value. So if I have this polynomial and these are my possible zeros, and I'm trying to find the x-intercepts, what I'm going to do is take each of these zeros right here and divide them into that polynomial using my synthetic division. Well, as you can see here, we have a 0 here, 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 and here. That means we have 4 zeros for this polynomial. 1, -1, -2, and +4. Those are the actual zeros, ±1, -2, and +4. If we were to graph that polynomial, these are the 4 places where that polynomial would intersect the x-axis. Alright, so let's take a look at another example here. We have y equals 2x cubed plus x squared minus 13x plus 6. So we are only concerned with the constant term and the leading coefficient. Factors of the constant are going to be ±1, ±2, ±3, and ±6. The factors of the leading coefficient are going to be ±1 and ±2. Alright, so this is going to generate our list of possible rational zeros, and we still need to simplify this down a little bit. So we're going to take 1 and put it over each of these denominators. So that's going to give us ±1 and ±1/2. And then we'll do the same thing with 2. Put it over 1, which is ±2. And then we put it over the 2. Well, 2 over 2 is 1, but we already have that in our list, so we do not need to repeat that value. Right, so now we go on to the next one. We're going to have 3 over 1, which is 3. And then we have 3 over 2, so it's ±3 over 2. And then we move on to the 6, so that's going to be 6 over 1 and 6 over 2. Now 6 over 2 is 3, and we already have that value in our list, so we do not need to put that in here anymore. So this is our list of possible rational zeros. We could actually find out where this graph does intersect the x-axis by doing the synthetic division like we did in the previous problem, using all of these values and try dividing it into this polynomial. I'm not going to go through that process because it's a little bit long. There are a total of 12 numbers in this list, so we would have 12 division problems to be able to figure out which ones are the actual rational zeros. Alright, so this next example is going to be a little bit different simply because we do not have a constant over here on the end of the polynomial. So if you do not have a constant to help generate this list, what you're going to do is take out a GCF out of this polynomial. We have an x in common here. So we're going to factor out the x, which leaves us with x squared plus x minus 6. Now, because we factored out this x, that means that 0 is going to be one of our zeros. Now we use the polynomial that is in the parentheses to generate a list of possible rational zeros from here. All right, so we have a constant of 6 on the end and a leading coefficient of 1. So that's going to give us plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, all over plus or minus 1. All right, so we can complete our list now. In addition to 0, we will have plus or minus 1 over 1, which is 1, plus or minus 2 over 1, plus or minus 3 over 1, and plus or minus 6 over 1. Now, these are the possible rational zeros. We do know that 0 is actually one of our zeros. So we would really only need to do the division, the synthetic division, with the remaining values over here to find out where the other zeros are for this polynomial.